Today I'm going to talk about how MEMS technology or micromachining technology is being used on quantum devices. Now there have been a number of approaches to making qubits or quantum computing bits. Two of the leading candidates would be the cryogenic CMOS approach that Google, IBM, and others have taken. A picture of one of those apparatuses shown here. You've got to cool the actual qubit down to 20 millikelvin. So it's a huge effort to cryogenically cool these bits. And as a result, the devices, the quantum computers are relatively large, room-filling large. So think ENIAC computer from the 1950s. It was cool that we had a computer finally with vacuum tubes back then. But it was impractical for all but government research and labs and big industry. So the goal that I would like to pursue, and I think others as well, is how do you make a quantum computer that can fit on your wristwatch? How do you have mobile quantum computing and mobile personal AI? And one technique that could work for that is using micro optical, electrical, mechanical systems to trap ions. These trapped ions are then used as the qubit. And so it's interesting technology that I'm going to explore in this talk and also explore some of the problems or challenges associated with this technology. So what are MEMS or what are MOAMs? MEMS stands for micro optical or electromechanical systems. It's a subset of the semiconductor industry. There are three-dimensional moving parts. There can be cavities, diaphragms, cantilevers, etc. They're used in microphones, motion sensors, RF filters. Your smartphone and your car are filled with MEMS devices. So it's not just a computer chip, it's a computer chip with small moving parts that may sense or vibrate or do other features. And the part that we're going to use in quantum computing is this bonding and cavity formation, mixing glasses and silicons together at the chip level. So for photonic quantum devices, we're going to use this chip scale packaging capability. We're going to be able to create a vacuum cavity, or maybe partially fill a special gas in that cavity, which will be the ion, and this cavity will contain the ion and allow it to float freely and become a qubit. It's going to need optical interfaces or windows. It's going to need electrical interfaces, and you're probably going to need heating for the metal vapor source. Atomic clocks were kind of the forebearer of the MEMS-based qubit. These were initially kind of hand-built using, they were called cesium atomic clocks back in the day. They used glass tubes filled with cesium. They would stimulate it with a rubidium discharge lamp. You use this frequency, a feedback loop to make this oscillate, and you get this very accurate timekeeping capability based on atomic energy levels. In the early 2000s, DARPA funded a project to accomplish this using MEMS. So very small chip-based approach to make a cesium atomic clock. They successfully did that. There's a picture of it shown here. This is the NIST device with these stacked chips wire bonded together on a circuit board. So what are the elements of a MEMS vapor cell, whether it's atomic clock or a qubit? Typically, most of the devices use glass, silicon glass bonding. The glass is the window for the laser beam. There will be, a laser beam on top, a photodetector on the bottom, and then you may have some metal electrodes to heat up the metal vapor. This could be heated up in an ionized, or it could just be heated up as a neutral atom. So those are the basic parts. 3 wafers bonded together using our old-fashioned micromachining or MEMS-based processing and design techniques. Now let's look at about wafer packaging or wafer to wafer bonding. So again, this is how we make these tiny qubit chips. This just shows you an example of, say, 2 wafers. This has a micro machine cantilever. You know, I've worked a lot on accelerometers and gyroscopes, which are cantilevers that are vacuum bonded using wafer-to-wafer bonding. A wafer-to-wafer bonder shown on the right, and an example of a bonded wafer stack, and maybe some chips that have been cut out of there, which we would call chip scale packaging, are shown on the bottom left. So there are ways to get the electrical circuit out underneath the seal, because you have to have a seal ring to form a vacuum. You have thin film getters, which absorb unwanted gas molecules. And then you may have in our case, we'll have an optical top cap. We'll have a glass top cap as the top wafer. And there have been a lot of wafer-to-wafer bonding techniques developed. They all require, for the most part, different bond temperatures. Some of them may be as high as 1,000 degrees C, which would be a silicon fusion bond. You bond it at room temperature, but then you have to anneal it. The glass to silicon anodic bond is shown there in the middle. That typically requires temperatures of 300 to 420 degrees C to get that electrostatic bond. There are solder bonds. There are adhesive bonds, which aren't really hermetic and can't be used in this case. And there's a number of eutectic or metal-to-metal thermocompression bonding methods that have been developed. Now, anodic bond, since that's the bond used on virtually all atomic clock and qubits so far, it requires you to heat up a sodium-doped glass next to a silicon wafer. 2 electrodes are applied. The sodium glass or sodium ions migrate under high temperature and high DC bias, several hundred volts, and the oxygen atoms will react at the interface with the silicon wafer below it and form this electrostatic anodic bond. It's a really good bond. The main weak points to this bond are if you get particles in there, you'll have maybe a void. So this is what we mean when we talk about anodic silicon to glass bonding. One thing to be aware of is this bonding generates a lot of oxygen. Oxygen is freed inside the cavity from the glass. And so this could interfere with your metal ions, and it could cause them to oxidize and lead to quantum decoherence. So that's one of the weak points or challenges that has to be overcome when dealing with this technology. There are other glass-to-glass bonding techniques, for example, glass-to-glass direct bonding, glass reflowed frit bonding. All of these have benefits and challenges as well. And this shows on the top left, we're showing how a getter film can be coated on the interior of the glass cavity, and this getter will absorb the oxygen atom that's generated from the process. And this glass micromachining technique allows you to do arrays. Multiple cavities, arrays of multiple cavities are commonly used in biomedical applications, in cell applications. So it's not uncommon to make multiple cavities which can be bonded together, and that allows you to eventually expand into an array of qubits. So just keep that in the back of your head. This is how one way that you could have multiple cavities, either through horizontal multiple wells etched in the glass, or through multiple stackings of wafers. Now, we talked about gettering just briefly. A getter is a reactive metal that, when heated, will absorb gases like oxygen, hydrogen, water vapor, carbon dioxide, carbon monoxide. And again, that's needed to prevent the neutral or ionized metal vapor from reacting with trapped gases. And gases, before the bonding, gases appear to the surfaces of everything. You can bake some of them off, but the bottom line is there's going to be some still trapped on those surfaces. When you bond the wafers together and form a vacuum seal, they're going to desorb and fill the cavity with a low pressure gaseous atmosphere. So these are eliminated through internal getters. The heat of the bonding process or a post-bond anneal can get rid of these, and you can electrically heat the getters as well to keep continuously purging the cavity of gases. Getters have a long history. They were actually developed in the 1890s for light bulbs and then used for vacuum tubes. They were then used in metal and ceramic packages and eventually used in wafer-to-wafer bonding. So if you're interested, I'm citing a text of an article I wrote about 10 years ago on, a century of using getters for electronic devices. So this is not a novel technique, but it can be, again, applied to qubits. Now, there's a certain chemistry with getters. You can get fizzy-absorbed gases. You can get chem-absorbed gases with getters. You can alloy metals to constantly rejuvenate the surface, pull the oxygen into the interior, rejuvenate the surface with new metals. That does require heating in addition to alloys. So there's a number of things to think about. Some qubits want to use buffer gases. So will the buffer gas react with the getter? You got to think about that as well. Ideally, you choose a buffer gas that would be a noble gas like argon, neon, helium. They won't react with thin film metal getters. Now, this is some work from a friend of mine that looked at a getter. I founded a company called Nano Getters, and he was evaluating these commercially. And he looked at pressure ranges that he got without getters, with just getters at bonding, and then with an outgassing step prior to the bonding step. And he was able to progressively push down the pressure range or the pressure of the microcavities using different manufacturing techniques. And the temperature of the bond will dictate the efficiency of the getter. So bonding like glass frit that's done at 400 degrees C may be beneficial to gettering out more residual gases that are trapped on the surfaces of the cavity. Now you can integrate getters so that they're incorporated into the wafer and still have an optical or infrared window. And this is an example of how we do this with infrared sensors. You put a border of the getter material on the perimeter of the infrared window, which in many cases is germanium or lightly doped silicon, and a shadow mask is shown here in the bottom left of an example of how you can use that to pattern an 8-inch wafer in this case, with a thin frame of getters that will effectively absorb the gases that are trapped. Now, heating is required in the current generation of vapor tubes. It might be possible in the future to use atoms that don't require as much heating, but right now we do have to heat them. That can pose a reliability issue. That imposes an electrical interface issue with this technology. And it's things that have been dealt with. We commonly make hot wire mass airflow sensors. This is a chip design on the right that I did, where you're actually heating up the platinum wires to enhance the flow sensing capability of that chip. Micro Menlo has developed a MEMS-based switch for power devices. So they have a vacuum cavity. It's an all-glass chip stack. They have through-glass vias. They pump a lot of current in there to heat it up. And they've been able to develop a pretty robust, reliable technique for making these types of chips with heaters. Now, one problem that I found early on in my career when you're doing vacuum packaging is that if you utilize it in a maybe an industrial gas environment where helium is present, this was a resonant flow sensor that I made, you can actually get helium leaking through wafer-to-wafer bond interface seals. And this shows up the quality factor. The quality factor is the sharpness of the resonator peak that's enclosed in the vacuum cavity. And we found that if we, in this case, whether it was silicon direct bond or glass strip bond, those seals would actually allow helium to permeate through the wafer-to-wafer bond on the chip scale package. And I did a wide survey of commercially available devices and devices that I made in the lab. A lot of techniques are permeable to helium. And the reason that's significant is the Earth's atmosphere has 5 parts per million helium in it. And there have been studies done at Stanford that some of these chips, if you heat them up, say 100 degrees C, which is not unheard of when the automotive applications, you'll get helium leaking in from atmospheres. So again, that can cause some quantum decoherence problems in a qubit. Now, I found that silicon to glass anodic bonding was really permeable to helium, unfortunately. This is just some data from a 2016 study that I did. This was a pressure sensor that used silicon to glass anodic bonding. We looked at 3 different manufacturers of this, and all of them leaked helium at this silicon glass interface. And this is key because most MEMS qubits made to date have used silicon to glass anodic bonding. So just something to be aware of. Helium is a weak point to this bonding technology. And here's a survey of all the different vacuum packages for MEMS that I looked at. Quite a few of them, if it says yes on this chart, that means under these high pressure conditions, whether it's 140 to all the way up to 690 kilopascals of helium pressure, you would eventually get helium leaking through the interface at room temperature. The only ones that didn't do that were Kovar soldered ceramic packages or welded Kovar metal packages. I was able to develop a solder bonding, wafer-to-wafer bonding process that didn't leak helium. So it is possible to have a chip scale package that's pretty much helium proof. So wavelength overlap. So as I mentioned, getters, thin film getters will not react with helium, argon, or neon. And just so you know, if you optically stimulate these gases, they will emit different wavelengths. So you just need to be aware of this. Like I said, helium leakage could lead to the wavelengths being absorbed on the left. If you're using argon sputtering to put down metals, that argon can outgas over time and temperature, and you might see some of the wavelengths on the right. So finally, just kind of getting into how do you integrate a package for a qubit? And these are just, again, ideas based on experience with other MEMS devices. In addition to gas issues at the wafer-to-wafer bonding level, you got to think about electromagnetic interference, EMC, electromagnetic pulses, electrostatic discharge, DC magnetic fields, and these have all been addressed using various metal shielding approaches. DC magnetic fields, this device was a nickel-based gyroscope that we found the nickel resonator frequency would shift if you got a magnet close to it. So we had to incorporate a mu metal shield. Those circuit boards show examples of Faraday cages that are soldered into the ground plane to electromagnetically protect the ICs under there. So quantum decoherence can be not only caused by gas atoms, it can be caused by temperature fluctuations, electromagnetic fields, DC magnetic fields. And so here's kind of a diagram I put together to think of all the techniques we used over the years to thermally, mechanically, electromagnetically isolate MEMS devices, kind of put them all together to show what maybe a packaged qubit would look like in a cross-sectional standpoint. You have your wafer-to-wafer bonded vapor seal, got your laser stacked on top, your photodetector underneath, maybe an IC underneath, an isolation platform that's micromachined for mechanical isolation. You don't want phonons being introduced into this if at all possible. It'll also be an insulating material. Maybe it'll have a heater integrated onto it. You could have the heater integrated onto the MEMS chip or onto this platform. You've got it enclosed in a mu metal Faraday cage, so you've got your DC magnetic field, you've got your EMC fields protected there. So this is just one idea. So in summary, MEMS wafer-level packaging is going to be a key element to making quantum chiplets, to making qubits that are mobile. Vapor cells can be essentially at room temperature. They can be heated with an on-chip element that requires, microamps of power or current. So that's one potential way to get to mobile AI, mobile quantum computing. I don't think mobile quantum computing has an option with cryogenic CMOS qubits in the way they're configured now. They're just too large, they're too power intensive. So there's a number of wafer level packaging challenges that have to be overcome or addressed to have a hermetic, reliable seal, to eliminate trapped gases, to eliminate a number of things, both at the chip and package level, that can lead to quantum decoherence. These include the trapped gases, magnetic fields, electromagnetic interference, things like that that can be addressed at the package and chip level. And these have been addressed at the package and chip level with other MEMS devices. Now, the challenges are harder for preventing quantum decoherence. There's no doubt about that. But I think there's a path forward with this. So look forward to seeing this chip level vapor cell being applied to arrays of cells on a chip. We could have essentially a quantum Moore's law going on here, where we're increasing the number of vapor cells per chip, shrinking their size, shrinking the memory, quantum memory chips, as you would say, using this design technique, using this MEM fabrication technique, and then building up these quantum chiplets, stacking the lasers, photonic devices, photoreceivers, MEMS chips together. Thank you very much.